Okay, so I think we're good to start. Now would be a good time to turn any cell phones on silent and stop any interesting conversations. So I'm very happy to introduce the next talk to you. I've recently also tasted from the forbidden fruit, which is static typing, fast tooling, great error messages, things we don't necessarily have in Clojure. And so I'm very curious to hear Andrew Mcveigh shed some light on the intersection of static and dynamic typing in his talk, A Dynamic Statically Typed Contradiction. Please give it up for Andrew.
So, say you've got a good-sized Clojure code base, all written in Clojure. That's great, right? That's where we want to be. But what happens when you need to add something to it? And perhaps the problem there is better suited to type functional programming. And more still, the kind of guarantees that you can get from a strong type system just happen to be the exact thing that you want for this feature. Should you just give up and start writing it in Haskell? Like maybe you need to implement a network protocol, say, or a parser, some kind of compiler. You can write these kind of things in Clojure, but the language doesn't really help you out very much. One of Clojure's core tenets is the language should stay out of your way as much as possible. But sometimes it gets so far out of your way that you get lost, and sometimes you really want the language to give you a nudge in the right direction. And we should be able to turn up the level of help we get from the language. In this case, I'm talking about static type systems. And I want to be able to turn it on where we need it the most. And we can avoid, say, the common pain points of working in the restrictive language the rest of the time. Now, this is a controversial topic. I don't know why. Is it just a matter of taste? I think it mostly is a matter of taste, but taste is informed by experience. And I ask a question of you. How many different type systems have you experienced? It's kind of almost the same question as how many programming languages have you used? What were the type systems there for? Are they there to help the compiler lay out memory? Are they there to help the programmer out? Are they there to enforce a design paradigm? Have you been able to separate a type system from a language, like, say, C's type system, or maybe Java's? What were they designed for? I don't think either of them were designed to make programmers happy. But what about Haskell? Haskell's type system really defines the language, and it defines a very different programming model to that of Clojure or any other dynamic language, and it can be very jarring at first, especially if you're used to thinking in the Clojure way. And you get a lot of criticism of type systems, and even the type theorists themselves have criticism. The criticism ranges from the type system provides very little to it's basically impossible to write a valid program. And there are problems with even the fanciest type systems. Like, the fancier the type theory used, often the less type inference can help you, and that means that you're writing more code just to satisfy the type checker. You might not be able to express an algorithm in the most natural style. And there are still correct programs that exist that are not well typed. But the whole point of Clojure being a Lisp is that the programmer can extend the language and not just the author. So what if we can choose which type theory to use, where it's appropriate, in the place where we need it? But if we just take a step back and understand where all this comes from, the lambda calculus, I'm sure you've heard of it. It's a formal system for expressing computation. And it's based on function abstraction, function application, variable binding, and substitution. And Alonzo Church first described it in the 1930s. And although Lisp or the original Lisp, was not directly based on the lambda calculus. It's clearly influenced by it. Church's work was referenced in the original Lisp paper by John McCarthy in 1959. It's a really simple language. It's just this. It says E, an expression, is defined as x or lambda.x, that's the function abstraction, or E applied to E prime, where E prime and E are both expressions. Now, the simply typed lambda calculus is a typed interpretation of the untyped lambda calculus. And again, Church introduced this in 1940. It was his attempt to eliminate paradoxical uses of the untyped lambda calculus. The syntax is more or less the same. You can see the difference is that the terms are typed. I'll try and point that out. There, x is of type t. Sorry, I can't reach that one. There we go. So that's the rule, that every function abstraction must specify the type of its argument. Now, Hindley-Milner based type systems have influenced many mainstream programming languages in recent years. And Milner's paper lays out, he defines a very similar syntax to the untyped lambda calculus. In fact, it's exactly the same apart from the fourth clause, the let expression. And here are the typing rules for those terms. There's one for each syntax element. And they take the form of proof trees from Gerhard Gentzen's natural deduction. And so what type inference is about is taking those typing rules and some untyped syntax and running the rules backwards to determine the type of the expression. But you might ask, how do you even run these things forwards? They don't look like anything I ever saw before. So usually we work from the top down. This is a typing rule for function application. And if we can say that the things on the top are true, then we can conclude that things below are true. And so if E1 on the left is of type T1 to T2, and E2 on the right is of type T1, then we can conclude that we have a function application that is of type T2. And that makes sense, right? If you have a function from T1 to T2, you give it a T1, you're going to get something of a type T2 back. And so running them backwards means we start from the syntax. So we know from Clojure syntax what a function application looks like. We know that we need to apply this rule. So how do we do that? We break it apart, and we start with the thing on the bottom, assume it is type T2, break it apart, and for that to be true, the function part, E1, needs to be of type T1 to T2, and the argument number 1 there needs to be of type T1. And if that's true, then the whole thing holds, it type checks. And if not, then it doesn't type check. And we go on, like throughout the tree of syntax, and work through the rules upwards. For the rule to be valid, the thing above must be valid, and so on. And that's really what type inference is about. And what's special about the algorithm that Robin Milner described, algorithm W, is that it's complete. And it finds the most general type of the whole programming language, of a whole program, sorry, not whole language. And the programmer doesn't have to write any of the types down. Now, Roger Hindley first described this algorithm in 1969, and he attributed it to Haskell Curry, who was said to be using it informally in the 1950s, possibly even the 1930s. So this is really old stuff. Robin Milner rediscovered this algorithm in the late 70s. And so type systems using an algorithm of this type are generally known as Hindley-Milner. Before we get to the algorithm itself, there are a couple of other things that we need to know about. So substitution is a syntactic transformation of expressions. We apply a substitution to an expression by recursively replacing all instances of, in this case, x with a. And they can be composed. The result of applying a substitution, a composed substitution, is the same as applying one after the other, just in the same way that function composition works. We also need unification. Both Hindley and Milner used Robinson's unification algorithm, and he developed it in 1965 for theorem proving in logic programming languages like Prolog. And unification is the algorithmic process of solving equations between symbolic expressions. And Robinson's algorithm finds the most general unifier of two symbolic expressions. The result of unification is a substitution, and we want to use this algorithm to find the most general unifier of two types. So when two types are unified, we can say that that type checks. Now, algorithm W is defined as, given a typing environment, it's represented by gamma, and an expression E, W succeeds if it finds a substitution S and a type tau. There are 4 cases to the algorithm, one for each syntax element. It's a recursive syntax tree walking algorithm, and it shares very much with the Lisp function eval. But rather than with evaluation, where evaluation of an expression returns a value, inference returns a substitution and a type. Now, as an example, you can see this tiny bit of Clojure code. It's obviously completely useless, but it is really easy to type. So it also contains all the cases of this algorithm. And here is that syntax represented visually as a graph. We can see that if we were to evaluate this, the first thing that we would come to would be the increment 100 function or application. And the second branch, the A, would be bound to that value. And it's the same thing in inference. We first need to infer that branch and then bind that type to the A. So if we walk the tree, inferring the types, here we're at application of the inc function. If we think intuitively, if we have a function of type A to B, and we have a value that we apply to that function of type A, we're going to get something of type B. And if we don't have that A, then type checking is going to fail. Now we walk down further the tree, and we get to inc. Inc here is a symbol, and if you think about what happens when you try to evaluate a symbol in Clojure, what do? You look up the symbol in the environment, and that's its lexical scope, followed by a larger scope, the namespace. And if you don't find it there, that's going to be an error. And so the same happens in inference. If we look up the symbol in the typing environment this time, if we don't find it, that's also an error. But in this case, because I cheat, we do find it. It's a function of type int to int. And so remember I said that every step of the algorithm, we're going to be getting back a substitution and a type. And here we need to apply that substitution to the type environment so that the types that we work out in the branch E1 can be applied to the branches in E2 and the rest of the tree. So now we need to work out the type of the argument. That's pretty easy. It's a literal value. We already know its type. It's an int. And when we have a function of type int to int and an argument of type int, the whole expression is trivially type int. All right, we're back to the top. We've gone down the branch E1. We need to bind the type that we found there to A. And we can start with the rest of the tree. We have here another function application. In fact, it's treated exactly the same as the previous function application. But this time we've got a lambda in the function position. We still do the same thing. We need to go down that branch. And this time it's a lambda, and it's the simplest one we can get, the identity function. But because right now we don't know the type of the argument, we have to guess. And guessing means just taking a fresh random type variable. And we bind that variable to the symbol x in the environment. OK, and the expression of the lambda was just an x too. And so we need to look up in the type environment that symbol. And so in doing so, we just bound that x to the type variable a. And so the inference of that is going to be that type variable. And now we know both the argument type and the function type. It is, so the type of the lambda is the function type alpha to alpha. And that's it. We've gone over all the 4 cases. We just work our way back up the tree, filling in things that we go as we go. And now, it doesn't matter for type checking, that we've already determined the type of the expression, but you can see towards the bottom right, the x's are still those type variables that we guessed at. But further up the tree, we worked out that those variables should be an int. And that information was returned to us in the final substitution. And so we can pass or substitute, apply that substitution all across the tree again to annotate the types of the variables that we only guessed at initially. And we've since defined the types more precisely. But right, that's not Clojure. That is Robin Milner's original type system, and it was designed for ML. So how does that fit Clojure? Well, the point of Hindley-Milner is that the programmer writes the syntax of the untyped lambda calculus without any type annotations, and the inference algorithm types the syntax according to those rules. But there is a subset of Clojure that is very close to the lambda calculus, and it might easily be typable if we can encode parts of Clojure in the simply typed lambda calculus. So the thing that people talk about when they talk about Hindley-Milner-based languages is algebraic data types. And we can encode pairs and sum types in the simply typed lambda calculus itself. But without something to differentiate pairs from pairs and sums from other sums, it's impossible to tell the structure apart. In fact, they're the same. But it is trivial to extend unification to products and sum types. You just need to check the structure and maybe a label. And type checking is going to be much quicker without all this lambda upon lambda upon lambda encoding. And you can type lots of different data structures with product types and sum types, such as lists, vectors, tuples, all kinds of trees. But when it comes to data, everything in Clojure is about maps. Now, there are these things called extensible records. They've been around for ages. I took a paper from 2005 by Dan Leyen. He adds extensible records to a Hindley-Milner type system, and it wasn't the first paper on the topic. Now, records are not as flexible as Clojure maps, but they're really not very far off. They're kind of about the same as clojure.spec's key specs restricts you to. But the other restriction is that you need to know what the keys are at type checking time. But as long as you do, the keys map to types and collect up in the type system in a similar way to how keys map to values at runtime. And so what other features of Clojure are we missing? Clojure is pretty big on ad hoc polymorphism. And together, protocols and multi-methods are very powerful. We have efficient dispatch with protocol functions and flexible multi-method dispatch based on the result of any arbitrary function. How can we type something like this? Well, I admit I have no idea how to type multi-methods, but we can do better than protocols. Haskell has type classes, or some language like Idris has interfaces, and these are also really powerful. They offer efficient dispatch on any of the types involved. That's any combination of the arguments and even the return type. So they might not be quite as flexible as multi-methods, but they're clearly more powerful than protocols, and they were designed for type languages. So I admit again, I've not quite matched all of Clojure's semantics with this type system, but I think it's much closer to Clojure than what we started with. And if we further extend it, we can probably get a little bit closer and still retain type inference. I'm not really interested in typing the whole of Clojure. We already have core.typed for that. I'm interested in this usable subset that can be typed in this way with full type inference. Now, I hope this works. You see that? It's a bit small. You read it at the back? Yeah. Okay. Ooh, that's weird. Anyway, so I've just annotated this namespace with a bit of metadata. This means that when I've turned type checking on, this namespace will be type checked. I've listed a few fairly naive type annotations for clojure call functions. I just want to give a demonstration of why you might use a type system. So I've just turned type checking off with a key combination. Typically in Clojure, you're going to write a function and evaluate it at the REPL. And then you might run it, and nothing happens. And that's because you got a runtime exception. And that tells me that string could not be cast to a number. But that was not anywhere near what I just wrote. That was all the way up here in this function. So there's not very good locality to sort of like using this dynamic define and then run paradigm that we use in the REPL. But if I turn type checking back on and try to define the function again, well, this time I got an error. I don't know if you see the little red underline. And it tells me that I could not unify long and string. Now, that's not really very descriptive. I haven't worked on error messages yet. I don't think people in this community are that interested in error messages, are we? But what it does do is it tells you exactly where this failure happened, and that's here. It's underlined in red, because I have the exact point where that unification failure happened. So I also have a demonstration of how extensible records work. This kind of just looks like, so the first part of the result is the value that we got from evaluating, and the second part of the result is the type annotation. You can see here that I haven't written any types, it's just picked that up from the syntax. The keys are mapped to types in the second part. We can see that assoc works in the way that you would expect, that the value is a map, and the type is a map that now has this extra key on. Dissoc, the same thing. It's removing a key and a type from the map. And lookup is doing the same thing. It's finding the type that you want to extract and displaying it. In this case, lookup fails. And the reason is that this record does not contain the row B, because on this line, I removed it, and then I tried to extract it from here. So in Clojure, without this type system, you probably get a nil at this point. But I'm not sure that's what really we always want. Here I'm just defining a constant for VAT, and a function that uses it, and another function that uses that function. And if I try to type check this function, what happened? Sorry. If I try to type check that function, it tells me I can't, and the reason is that the record does not contain the label xVatTotal. Where did that come from? And that's picked. The type system has picked up that I tried to use xVatTotal here on this argument. I haven't had to write any of these types down. It's just worked it out. And if I supply to the function a value that does have that there, then it's fine. And the type system and extensible records are not going to make any assumptions about the types of things it doesn't care about. So in this instance, I've got the value something else onto the map but add the final total doesn't care about that. But the value is still carried through in Clojure, and the type system keeps the type around afterwards as well. So that if you needed that something else, it would still be there to evaluate and type check. So you can also use the type system to tell you things about what data you have or what your function is returning. You might have like, I don't know, say a database call that returns you a huge map, and if you try to display that on your screen, it's going to blow up. But you can just ask what the type of this expression will yield, and even if I take A from that, what type of thing that is. So you have this like extra level of information that you can ask of the type checker. You can also ask in your syntax, like, what is the type of this thing? Like, you might get a deeply nested piece of code, and you don't know what this thing is that you're looking at, and you can just ask, like, what is this syntax element? Or what is the type of this function? You have this kind of logical interpreter that's running in the background that you can ask questions of. Like, a trivial example is I have this list of eithers, and I want to map over them, but I don't know like what the function is called that I want. So I can see what the type of the thing should be, and it can help me think like, what should the function I want? No, that's not how I want to say it. Let's forget about that. So in this case, I have another list of eithers, but it's a bit more complex. And again, I want to map over it, but I can't remember the name of the function, so I might as well just ask the compiler, like, what kind of functions would fit here? And if the answers are few enough, why not just fill it in? And then, of course, it works. You can also do other things with the type system. Like this, it's a common practice in Haskell and other type languages, is that you create a data type, and the only way you can construct that data type is to use a certain constructor. So you can validate the input, and you know that once you have an element of this type, it must be valid. So you can try to do it on something that's not real, but you won't get a valid answer. Or you can try to do it something that does validate, and you get the thing that you asked for. But it can be a pain to kind of unwrap these things all the time. So we might want to define a coercion between, say, an email address and a string for when we want to output it as JSON or whatever. And here we define a coercion from email to string. It's pretty easy. We're just unwrapping the email and then returning the string. And here I'm just defining a function, mainly for the purpose of this demo. But I specifically add the type annotation here. But that's not to satisfy the type checker. It's because I want to use that type annotation to inform how the polymorphism should behave. Of course, no demo of a type system for a functional language would be complete without an implementation of a monad. So here's the maybe monad instance. It's more or less a copy-paste from the Haskell source code. And this is monadic do notation in a two-line macro, so Clojure is still really powerful. And this is an example of quite complex polymorphic behavior. We're first taking an email, and the monadic do notation is kind of looking under the maybe monad and binding the value email to this actual email, and then it's going to try and coerce that email into a string using the above return type polymorphism. And then again, return here is also polymorphic in the return type, but it's polymorphic in the type of the monad itself, not in the type of the value. So you can see that's pretty powerful. And I've come all this way and not answered this crucial question. You might be wondering, hopefully you know, but what even is a type? And what can have a type? So values and expressions have types. Programs have types. Types themselves are based in formal logic. They have a syntax to describe them. There's kind of an interpreter that reasons about your code. And they work at the unevaluated syntax level. They describe properties of your programs. There's this kind of declarative logical meta-language that ensures your program is consistent with the properties that you describe. So I don't think it's very smart to turn our backs on types. I want types to work for Clojure in a way that we want, to enhance, not restrict our workflow. And as a community, we've always been willing to steal bits of other languages and research and implement those ideas, even just at a library level. And so much great work and research going on in typed languages, but it doesn't really make sense without types. But I want some of that. And I hope I've shown that you can embed a differently typed language in Clojure and as a library. I think there should be sort of a volume knob for types where the programmer can choose the level, and Clojure's default might be lower than something like Haskell, but we should be able to turn it up as well. Thank you. Thank you.
Thank you very much, Andrew. And I think we might have time for one or two questions if anyone wants to poke a hole into Andrew.
Hi.
Hey.
First of all, bloody brilliant what you've done here with the types. I assume this is a library, right?
Not yet. No.
Not yet. Jesus, okay. But just out of curiosity,
yes.
How do you actually equate two types? How do you make sure that a double is equal to a double?
Okay.
I don't think it's just naive string comparison.
Not exactly. So unification is what you compare two types with. There are 4 basic rules. So constant type, like a double, you say, and a constant type only equate if they're the same. Variable type variables, like I sort of referenced earlier, those will unify with any other type. So when you unify those, they kind of bind to that type then, and then get carried up further in the algorithm. Structural types are evaluated first by like the type of the type. So list would compare with list, and then the structure needs to be the same. So it's kind of like a whole bunch of different rules to equate two types. Yeah. If you want to look up, any unification implementation for a programming language, it's a fairly straightforward algorithm. Yeah.
Thanks for the question.
One of them.
Yep.
Yeah, thanks for the talk. So I don't get to program as much as I would like to in Clojure, but I had it occur to me a bunch of times that I would really like to have types because it's something that I appreciate as a part of my workflow. So why did you build this, and when will you release it as a library, please?
So why was, I don't know, I've been thinking about this for at least 2 years. I wanted something that would tell me about like what functions or what I can rely on in Clojure when I come to a function that I don't know what it is. And you know, Clojure functions purport to be pure, but often it's a lie. Like you don't know exactly what's going on under the hood. And I would like that somehow reflected in a type system so that I can kind of know what I can trust. Second part, when is it going to be a library? The code is available somewhere on GitHub. I'm purposefully vague because it's pretty bad. And it's going to be a bad experience if you try to use it right now. I want to set expectations. You're going to have to know a lot about REPL and how to debug type errors in code that's already buggy. So like maybe 6 to 12 months. Yeah.
Okay. Do we have any more questions? but make it short.
What's the performance implication of using this?
Well, in at runtime, none. Like it's not involved in runtime at all. The thing that could be an implication is that when you have a type system, you tend to wrap things in types, and wrapping arbitrary numbers in a def type is going to incur a small performance problem. But like compared to a map, it's smaller than a map. So like if you encode types in maps, it's going to be more expensive than encoding types in a type. So at runtime, none. Please, no one prove me wrong.
Okay, so thanks everyone for the question. Once again, thanks to Andrew for giving this fantastic talk.
Thank you.